Hello, George Romanic here. In today's video we are going to investigate collision frequencies among atoms in an ideal gas, such as air that is surrounding us. Towards the end of this video you will see numbers that our brains cannot comprehend. The numbers are so enormous that our intellect is simply not ready to visualize something like that without properly understanding science behind it. And that's why we study natural sciences, to be able to, at least to some level, comprehend what is happening in the universe around us. After this video, you will look differently at the air around you. You will visualize collisions among atoms and molecules in that air differently, because you will see what is happening every single second of our lives. And what is happening is complete chaos in terms of collision frequencies between atoms in air. Mean free path from our previous video was equal to k times t divided by square root of 2 pi p d squared, where k is Boltzmann constant 1.38 times 10 to power negative 23 joules per Kelvin, T is absolute temperature in kelvins, P is pressure in pascals, and D is diameter of atoms. Mean free path, lambda, is the average distance that particles traverse before colliding with other particles. So if we have a lot of particles here in the gas, we demonstrated that on average, they are moving, of course, in any given direction. Our previous video demonstrated that this lambda is average distance that any of these particles will traverse before colliding with another particle. Yet in another video, we found that the mean speed of these atoms is equal square root of 8 times k times t divided by pi m, where m is mass of an atom. So logically, we can therefore combine average distance traveled with average speed to find the average time between collisions, and that's tau. And that average time is obviously average distance divided by average speed. This quantity is the average time between two collisions in a gas. Of course, I can now substitute lambda and V average over here, and in that case we get that tau is equal square root of mkt divided by 16 pi p square diameter to power 4. Let us circle this beautiful result that follows from kinetic theory of gases and ultimately Newton's laws of motion. Now, because this time is mean time between any two collisions, that means it's repetitive time. Therefore, we can define something called collision frequency, which is average number of collisions per unit time. And for some reason, many books use capital Z to represent that collision frequency. So Z is collision frequency, which of course, as any frequency, is 1 over period between two collisions. And that is therefore equal, if you want, of course, from this formula, mean V over lambda, or you can inverse this formula to get square root 16 pi p squared d to power 4 divided by k times m times t. I calculated here mean time between 2 collisions for some typical gases in our air. I included radon too. So nitrogen, for example, is 78% of air. Most what we breathe is nitrogen. So mean time between 2 collisions in seconds for nitrogen atoms at room pressure and room temperature is order of magnitude 10 to power negative 10 seconds. That is astonishingly small number to think about. It gets even better if we look at the same phenomenon from the point of view of collision frequency, that capital Z that I introduced in 1 per second or hertz. If we go back to nitrogen, notice that there are order of magnitude 10 to power 9 collisions every second. If we count 1, 2, 3, 4, 5 every second in air around you and me, there are billions of collisions of nitrogen atoms. If that is not breathtaking, I don't know what it is. And you can see that numbers are extraordinarily large for any gas in this table at these room values of pressure and temperature. Finally, we can also work out the total number of collisions per unit volume and unit time interval, because we already have the collision frequency between 2 atoms. Then collision frequency for n particles will simply be n times this capital Z, and this is usually called small z, but we also have to add 1 over 2. Why do we have to add 1 over 2? Well, let's think about it. If we have this gas with these atoms like so, let us just, for the sake of simplicity, split this figure in 2, like so. And now let us say that atoms in this, this is not left, in this right portion will collide with atoms in the left portion of this gas. Well, collision between right atoms and left atoms in this box is the same as collision between atoms from the left side and atoms from the right side. And that means we don't want to count one collision 2 times, and that's why this factor of 1 over 2 is added to the total number of collisions. Of course, we don't like to work with a number of particles per unit volume, so what we can do is use equation of state for an ideal gas that says pressure times volume is number of atoms in that volume V times Boltzmann constant times absolute temperature. Or I can say P is equal N divided by V, but N divided by V is this N, small, times K times T. So this small n is not number of moles that chemists are using, but here in this context, number of particles per unit volume. So now when we combine this expression for Z and express N from here as P over KT and plug everything here, you will see that small z is equal 1 over 2 times n, and n is P over KT times capital Z, and that will be square root of 16 pi P squared d to power 4 divided by KMT, or if you make this to look nicer, you will get that Z is equal square root of 4 pi P to power 4 d to power 4 divided by K cubed temperature to power 3 times M. And this is total number of collisions per unit time and per unit volume. I calculated this quantity too, and you will see that number of collisions in 1 second in 1 cubic meter is just a number that our brains cannot comprehend. If you take this same nitrogen, 10 to power 34 collisions in 1 second in 1 cubic meter is something we cannot comprehend. But we can sit here for a few seconds and admire this number and the beauty of kinetic theory of gases. Because you can look in front of you and imagine 1 cubic meter of air. And in that 1 cubic meter of air, every second there is approximately 10 to power 34 collisions of nitrogen atoms at this pressure and this temperature, or even more collisions of hydrogen atoms, and so on. So the numbers are really something astonishing. This is really good table to bring with you to disco clubs, because this is perfect way to impress girls over there. If you go to disco club and you say, look, pressure is 1000 millibars, temperature is 23 degrees Celsius. Did you know that most probable speed of nitrogen in air that is hitting your glass of beer is 420 meters per second? Who wouldn't be impressed? How else can you impress someone? What do you say? Can I buy you a glass of drink? That's lame. That's as good as other guy. Go there, say radon. Relative speed between 2 atoms of radon is 240 meters per second. And that is just beautiful. During the preparation of this video, when I was calculating these enormous numbers, I always have a feeling perhaps this theory is not right and I made a mistake. There is no mistake. The numbers are crazy and they don't have to make sense to us because the universe doesn't have to make sense to us. We can sit here and enjoy the beauties of our universe through natural sciences such as atmospheric sciences. Until next video, goodbye.